Hi, um, welcome to the IFOA virtual conference. This is the first time I'm recording a video. I feel like a YouTube blogger. So I'm Jonathan Schwartz. I'm an actuary in Israel. I work in general insurance. I'd like to present in the next few minutes a project, a data science project that I built. So we have the video, which I pre-recorded. Then we have a few links that will be added in the description, I guess. So we have the first link is it's a notebook that's shared in RPubs, which has all the code and a few graphs, which we'll go through. The second link is a Shiny app where you can look at predictions. And the data that I use will also be available. So the data science project that I'd like to present to you is a project of predicting the probability of a severe bodily injury in a car accident in Tel Aviv. So a major part of actuary's work in general insurance is in motor insurance, and it's understanding the risk factors that affect the likelihood and severity of car accidents in order to be able to price motor insurance. So just a little background, in Israel in 2017, we had a big pricing reform on motor bodily injury. It's two different policies in Israel, the property and the casualty part. And there's a lot of strict regulation regarding the risk factors which could be used. You can't use any risk factor that you want. And that frustrated me that I couldn't build the best model that I can, only the model with the variables that are allowed by regulation. So I said, okay, then I'll build a better model as a project for fun. So every accident that has a bodily injury in Israel has to be reported to the police, and then a very reliable database can be put together, and there's one available by the Central Bureau of Statistics, and this data was made available for me, and basically this project is based on that data. Because we don't have the exposure of how many rides there were, this is going to be analysis of severity. So basically, for every car accident that was recorded with a bodily injury, we have the date, location, severity, type of vehicle involved, and many other factors. And this allows us to build many hypotheses on the severity of an accident. So what I'm trying to do here is to predict the probability of a severe bodily injury. So we'll dive into the data in a second, and we'll see that there's harsh accidents and light accidents. And we're going to try, based on variables that we have, with the most interesting one being location, to predict the probability of a severe car accident. So just a short layout of what we're going to be talking about. So we have a few descriptive statistics in the data. We'll be looking at geographical data. We'll be presenting it on a map. How I modeled the data, the models that I picked, that I decided to use, so model selection, and then we'll have the Shiny app to present the predictions. So I think we'll start from the end. We'll start from the Shiny app, which makes this very, very clear, and then we'll dive into how it was actually built. So if you're familiar with Shiny, it's I guess part of RStudio, and lets you build interactive apps for presenting data and predictions. So as I said, we're predicting the severity of a car accident in Tel Aviv. Just because that's the data that I used. I actually had for all of Israel, but just for simplicity, I started with Tel Aviv. So what you do here, so you go into the dashboard, and you decide what type of vehicle you're going to be riding. So in the model we have bicycle, motorcycle, private vehicle, or other. So let's say we do bicycle. We pick the hour of our accident. So let's say 3 o'clock in the afternoon. If we're in an intersection or not, so we're not in an intersection. If we're in a holiday or weekend, and then we put the address. So this is the address where I used to live. And if we click on the red dot, we see the probability of an accident, so 0.014. But if, let's say, we were at 9 o'clock at night, then the prediction would be 0.028. And if we were at a different address, say number 20 in that street, and then we were to be in the intersection, then the probability would go to 0.135. And if you would switch to a private car, then this probability would probably drop to 0.059. So basically based on the location, which we can put at any location in Tel Aviv in the model, and the day of the week or holiday or not holiday, intersection, which is another variable, time in the vehicle, we can predict the severity of an accident. Alright, so let's talk about the libraries that I used. So ggplot for graphs, dplyr for using data, plotly for interactive graphs, our pivot tables to make interactive pivot tables, leaflet for for maps, read Excel to read in the Excel, MGCV to build GAN models, and random forest to build random forest tree models. So first step is loading the data. Data will be available for you. It has all our variables. This I cut into a single year, 2011, a single city, Tel Aviv. So what type of data do we have? We have the date, the month, the day or night, the day type, which will be a holiday or not, the hour band, the hour itself, the severity, whether it's an intersection, the name of the street, car type, the the locations, we have longitude and latitude, the coordinates, etc. So here we have just a little bit of data munging, turning all the factors into weekdays or weekends, whatever, and let's jump into some descriptive statistics. So here we have Plotly, which gives us interactive graphs. So we're looking at the distribution between light and harsh accidents. We can see that most of our accidents are light accidents, and we have a very small, about 1 or 2%, that are harsh accidents. We can look at distribution between time of day, morning, noon, afternoon, evening, night. We can look at the distribution between days of the week, so we have most of our accidents are in the middle of the day. So again, remind we're talking about the severity, not the frequency. We don't know how many rides were on each day. Of course, in Plotly we can zoom in, which isn't very interesting for our bar plot, but there are certain plots where it is more interesting. Distribution of intersection, non-intersection. So most of them aren't in intersections, most accidents. We can look at the type of day. So Friday or the day before a holiday. Hol HaMoed, it's in certain Jewish holidays you have days that are a holiday, but people, it isn't a sabbatical day, and then we have the weekend and all the other days. So most of the accidents are on regular weekdays. Okay, now we're moving into representation of geographical data. So the coordinates that were given in the original database were in a structure called ITM coordinate system. So they're marked in X, Y. But all mapping packages that I know work with WGS 84 coordinates, which is the regular GPS coordinates. So we have to convert IDM to WGS 84. This isn't a straightforward task because the Earth isn't flat, so you have to do some sort of projection. Luckily, somebody wrote some Python code which does this. So the links are available where you can see how this was done. But I just, when I pre-processed the data, I translated the XY into latitude and longitude. So this we can look at the distribution longitude, and this is always confusing. So longitude is east to west. So we can see that most of the distribution is here. Because we're in ggplotly, we can of course zoom in if we would want to. And if we look at the distribution of latitude, which is north to south, then we have this distribution. In a second, I'll show you how it looks on the map, and you can see that this distribution kind of makes sense with how the map looks. So this is a single dimension distribution of a two-dimensional variable. Okay, so now we're presenting it on a map. We can see that we have this center distribution in this part. We're going in the north to south, and we have this distribution in this part when going west to east. So the red dots are the harsh accidents, and the blue dots are the light accidents. And we can zoom in. This in Leaflet works on OpenStreetMap. This isn't built on Google Maps. And because we have over 10,000 dots, it doesn't work very fast, but we could move the map around and zoom in and zoom out. Okay, let's continue with our data. So this is a package that I like called our pivot table, where basically we can use pivot tables in our environment. For most actually, they're very Excel heavy. What I don't like about this package is that you can't add a few statistics into the same pivot table, which you can do in Excel, which is kind of annoying. But let's just take an example from here. So we're looking at the severity percent. So how many harsh accidents out of light accidents we have. According to all kinds of variables, so we have the accident type. So we have collision back to front, collision back front to back, collision front to front. And we can see that, for example, collision with pedestrian has the highest probability of a harsh accident, or with stationary object. What we're missing here is the exposures of how many accidents we have in each group, which we can add, flipping over, or which we can add separately, but we can't put it in the same arc pivot table. We can look at another plot, another pivot table, which would look between intersections, so we can see that the probability on intersection is much higher than non-intersection. Of course, we have much more accidents that weren't in intersection, but when we look at how many harsh out of that were or weren't intersections, we have this probability. Alright, here we have another map where I filtered just the intersections, just to see how the distribution looks like. We can zoom in, we can zoom out. We can move the map, we can see that we're only on intersections. Alright, now we have another pivot table by type of vehicle. So we have bicycle, which is higher than a private car, almost double, motorcycle, which is a higher. And we can notice that we have an unknown category. So we'll see below how many, but we have a lot of unknown vehicles. So in order to build our model, we'll fill in these unknowns by predicting a model learned from the data. Alright, so let's go into modeling. What I like to do for geographical data is to have a GAM model. So it's like a general linear model. But here it's adaptive, and we can add splines or smooth variables. So just as an example for a model, so we would take severity. It would be a function of a smooth latitude, intersection as factor, an hour as a smooth variable, and date type as factor. And we're doing a binomial model because we're trying to predict our probability. And then if we look at the coefficients, our intercept is significant, our intersection factor is significant, our data type is significant, and we have our smooth variables, which are also significant. In order to build our final or more advanced model, we'll want to fill in the missing data types. So I chose to use a random forest classification model in order to fit in the unknown. And basically, I'm building a model using all the available data to predict, based on the known features, what type of vehicle you are. So you can look in the code to see exactly how I built the model. But then I predicted the unknown into different categories of vehicles. So I called the final type final car. And you can see that unknown, we have a total of 810. So I predicted 450 private, 298 other, 59 motorcycle, and 3 bicycle. Now that we've filled in missing data, we can build our final model. Here I took a look at the severity based on the type of vehicle after I filled in the unknowns. So now our second model, which is the final model that I used, is also a binomial GAM model. And here we took smooth variable of longitude and latitude together. So we're doing two-dimensional smoothing. I'll have a graph on the bottom that explains exactly what it looks like. Using intersection as factor, we're using hour as a smooth variable, and date type as factor, and the type of car. So basically the variables that we see here. So we're building the model that will be used in this Shiny app. So we can see that everything is significant, almost everything is significant, and the smooth variables as well. And we saved this model as M4. Here we have a three-dimensional graph showing the prediction based on longitude and latitude. So this is basically a map of Tel Aviv, where we can see the areas where the risk is higher and lower. And basically this is the effect of the location on the risk, and we did a two-dimensional smoothing. Now, this is kind of hard to understand what's going on because we don't have the map under it. So what I did over here is I predicted on our data the severity based on location. So I picked levels for every other variable, and I fixed them, and I ran all the locations as a grid, and then I colored the predictions according to the severity. So blue is a very low severity, and yellow is a very high severity, and this is the scale, and we can see just the effect of location. So you can see that northern Tel Aviv, especially the intersections, is a higher risk than the center of Tel Aviv. So if you've been to Tel Aviv, you know that people here drive faster because it's a more suburban area. And here there's a lot of traffic and you can't drive very fast. I guess that affects the severity. You can see that intersections are higher probabilities. Main roads have higher probabilities, and this is just the effect of location. So as somebody who lives in the city, it's interesting for me to know, okay, where's the more dangerous part of the city? Where's a higher chance that if I would get hit by a car, the accident would be severe? And then we can go back into our Shiny app and look at some predictions. So let's look at a different address. Alright, so I put in another address. This basically how it works. So we put in the text, and then we have this geocoded. The geocodes latitude and longitude, and then we have type of vehicle, so it's like a bicycle. We have the hour, we have intersection or not, weekday, yes or no, and all these feed into the model that we saw here. We then get a prediction, and then we present on the map the address that we put, and we can click on that dot. We present the prediction based on these features that are fed into our model. So if we would say put Noah 6, and then we would put an hour of 9 a.m., and we would be in a private car, then we would get this prediction. And if we would switch to not a holiday, we could see how our risk will drop significantly. So this is an interesting way, in my opinion, to build a Shiny app, because when you work with maps, you get a visualization, which, in my opinion, isn't very trivial. It's interesting to see these types of models. So location isn't a variable that may be used under the current regulations of Israel, so I kind of had to build a separate model just so I could feel good about myself when building models for pricing motor bodily injury. So we have a few conclusions about what vehicles are more dangerous. I suspect the bicycles are more dangerous than other vehicles. Later hours of the day are more dangerous than the earlier hours of the day. Center Tel Aviv is safer in the northern and southern parts. Further investigations that could be done here, which I haven't done yet, is to apply to all of Israel and not just Tel Aviv, to use multi-year data, maybe cross-reference with other databases such as weather database, in order to add more explanatory variables. So thank you very much for tuning in. I'm Jonathan Schwartz, actually from Israel. Feel free to play with a Shiny app, to go over the code, to play with the data. And if you have any questions or comments, then feel free to drop me a line. Thank you.